So in this video, I'll discuss how to distinguish between the Arrhenius and the Bronsted Lowry acids and bases. And so in order to distinguish the two, you want to be able to determine what makes it an Arrhenius base and what makes it a Bronsted Lowry or acid as well. And so when we're talking about the Arrhenius acid and base, you have to think back to discussions on electrolytes. Recall an electrolyte indicates that when a substance is dissolved in water, it will dissociate or break apart to form ions. This is what happens with Arrhenius acids and bases. These are based on how they dissociate. When they dissociate to produce specific ions, that allows us to determine whether or not it's an Arrhenius acid or an Arrhenius base. So for instance, when the compound dissociates to produce the hydronium ion, and we get hydronium by having a proton in water. So in other words, if it produces that proton, it's going to be an Arrhenius acid. So I'm just going to abbreviate it A acid. However, if that compound dissociates to produce hydroxide, and recall hydroxide is a polyatomic anion, then it's going to be an Arrhenius base. And so with the Arrhenius acids and bases, we're looking at how does it dissociate. Regardless of whether it's a strong or a weak electrolyte, it will produce ions. So if one of those ions is the proton, the hydrogen cation, or one of it is hydroxide, we can then classify it as an Arrhenius acid or an Arrhenius base. So for instance, if we had the compound potassium hydroxide, potassium hydroxide is soluble in water, so we can show it aqueous. Once we know that this ionic compound is soluble in water, we know it's a strong electrolyte. So it's going to completely dissociate and break apart into the ions that made up the compound, which would be the potassium cation plus the hydroxide anion. So because this substance broke apart to form hydroxide ions, this would be an Arrhenius base. So we can do the same thing with other compounds. So for instance, if we think back to sulfuric acid, so the name kind of gives you a clue as to how it will behave. But when we take sulfuric acid and we dissolve it in water, because this is a strong acid, it will completely break apart to produce the ion the first time it breaks apart. So it loses one ion. And then we have the hydrogen sulfate ion. So these are the two ions that are produced. So because we produce this proton, and if I show my physical state, it will be aqueous. Because we have this proton in water, which is the same as hydronium, because it produced that ion, then this will be classified as an Arrhenius acid. So again, with the Arrhenius acid and base, it's simply a matter of whether or not it breaks apart or dissociates in order to produce these specific ions. If it produces a proton when it dissociates, it's an Arrhenius acid. If it produces hydroxide when it dissociates, it's an Arrhenius base. And when we're talking about the Bronsted Lowry definition, we have to think a little more. So the Bronsted Lowry definition, we're not dealing with how it breaks apart or what types of ions it forms, but instead with the Bronsted Lowry definition, we're only focused on one ion, and that one ion is the proton, which is your hydrogen cation. So we're only concerned about this hydrogen cation. With the Bronsted Lowry definition, you're looking at your acids losing or donating that proton. So it'll give up that hydrogen ion, and then something else will accept it or gain it, and what accepts or gains it is the Bronsted Lowry base. So it accepts or gains that proton. So with the Bronsted Lowry acids, we're looking at how the proton is transferred. So we're looking at transferring that proton. What loses the proton is your Bronsted Lowry acid. What gains the proton is the base. So with the Bronsted Lowry acids and bases, we're actually looking at a reaction that takes place. Whereas with the Arrhenius acid or base, we can just focus on that single compound and look at how it dissociates. However, in order to transfer, if we think back to the law of conservation of mass, also known as the law of conservation of matter, atoms are neither gained or lost. So we can't just say that we got rid of or we lost this proton, but instead it was transferred. When something lost the proton, something else had to gain it. So with the Bronsted Lowry acids and bases, we're looking at reactions that take place with these substances. So you can look at a reaction, you have your two reactants, you can determine based on the substances that are present, which one is more likely to lose, which one is more likely to gain. And that goes back to pKa, which was in a different topic, a different lecture and video. But the pKa tells us how easily will this acid lose a proton. The easier it is for it to lose a proton, the more likely it is that it will act as the acid in an acid-base reaction. So for instance, if we have the following reaction, HCN plus water, so you can be given the full reaction. You can look at comparing what happened before and after that reaction took place in order to determine which is your acid and which represents your base. And so when you compare what was present on the reactant side to the product side, if you recall, when acids lose protons, they'll form a conjugate base. When a base gains a proton, it'll form a conjugate acid. And so in this case, we can look at the formulas of the substances that were present before and after that reaction took place to determine which one lost and which one gained. So you want to look for similarity. So we had HCN on the reactant side. On the product side, we see CN minus. So we know that these two are related to one another. And so this HCN, in order to go to CN with a negative, two things had to take place. First, you had to lose hydrogen. There was a loss of hydrogen, loss of one H to go from the reactant to the product. The second thing was the charge decrease. So the charge decrease. So what this tells us is that we lost a proton. A proton is a hydrogen ion. When you lose a proton, the number of hydrogen decreases, the overall charge decreases. So because HCN lost a proton, that lets us know that HCN represents our acid. So HCN is the acid, or more specific, is the Bronsted Lowry acid. We can then compare, we'll put the line above this time, H2O and H3O plus. So two things had to occur there. Again, we see a change in the hydrogen, we see a change in the overall charge. So we saw a gain of H, or an increase of H, so it went up by 1. We saw that the charge went up by 1. When a substance gains a proton, the number of hydrogen and the charge increases by 1. So what this tells us is that water served as the Bronsted Lowry base. So when you're looking at a Bronsted Lowry acid or base, you're simply comparing how the transfer of the proton took place. What lost the proton during that reaction, what gained the proton during the reaction. So we generally focus on the Bronsted Lowry acids and bases with chemical reactions, whereas the Arrhenius acids and bases are really looked at when we're dealing with solutions, because we can focus just on that one compound and how it dissolves in water. So we can focus on how a mixture is made with that compound. Will this mixture be acidic, meaning that when that substance dissolved, it's going to form the acid ion, which is the proton or hydronium, or will it be basic, meaning that when it dissolves, it will produce the hydroxide, which represents a base. So I hope this helps. If you have any other questions, please let me know. Thank you.